We can imagine light as a wave, but the distance between the crests of the wavelength, varies. And the longer the wavelength, the redder the light looks to our eyes. The shorter the wavelength, the bluer the color appears. So we see a spectrum of colors from red through yellow and green to blue. But there are colors outside this visible spectrum, longer wavelengths beyond red and shorter wavelengths beyond blue, colors that we can't see. The part of the spectrum that we can see is tiny compared to the whole. We're going on a journey to explore the whole spectrum. A journey that will take in science, art, nature, and technology. And using the latest technology, our journey will take us beyond the limits of visible light to the realms of the invisible. We'll start our journey with colors that are familiar, with visible light. For a long time, no one understood how the miracle of vision worked. They thought the eyes emitted something that illuminated what we saw. But Leonardo da Vinci showed that rays of something must be coming from objects and into our eyes. This was a huge step forward, but what was that something? It's light. And we know now that light behaves like a wave, with crests and troughs, like a wave on water. The distance between the crests of the wavelength, gives light its colors. Leonardo was partly right, but couldn't explain how we see different colors. 170 years later, Isaac Newton began to unravel the mystery of color. Newton passed sunlight through a prism which split the light into a rainbow of colors. He said that sunlight, white light, must be made up of different colors combined together. Others said the prism was coloring the white light. So Newton reversed the process. He passed his rainbow of colors through another prism and turned the rainbow back to white light. He'd proved that white light contained all the different colors. At first, Newton described just 5 colors in the spectrum. But then he thought the spectrum could be linked to the musical scale of 7 notes. So he added 2 more colors, the colors of the rainbow that we recognize today. But there are far more than 7 colors in the world. How do we see so many different colors? The human eye has only 3 different color sensors: for red, green, and blue light. Very similar to how this camera works. Sensors inside the camera also record the levels of red, green, and blue light. Combining red, green, and blue light in different proportions means the camera can recreate millions of subtle colors. And our brain does the same, combining the levels of red, green, and blue light seen by our eyes. To explore this world of color, we start our journey in the middle of the visible spectrum. Yellow. Nature is full of bright yellows, from flowers to butterflies. All these yellows are created by chemicals called pigments. Pigments are made of complicated molecules. These are packed into each scale on a butterfly wing. When light hits a pigment molecule, its energy makes electrons vibrate more strongly, and the energy of the light is absorbed, so the light disappears. But in most pigments, only some colors are absorbed. Other colors are reflected, giving the color we see. The color of the reflected light depends on the exact structure of each pigment molecule. Different pigments have molecules with different structures, so give rise to different colors. So, the varied colors of butterflies depend on different shaped pigment molecules. And one particular butterfly shows how even a small change in the pigment's chemistry can make a big change in color. This is a marbled white butterfly. The white patches on its wings contain a pigment that reflects all the wavelengths of light, so appears white. But change the chemistry and change the color. Soak some cotton wool in strong ammonia solution and place it in a closed dish. Then put a marbled white in the same dish and watch the transformation. The ammonia reacts with the pigment molecule, changing its structure. Now it absorbs all light except yellow, which it reflects. And the butterfly turns yellow. Nature is rich in yellows, but we can't take yellow for granted. Modern cameras capture this scene and printers reproduce it accurately. But in the past, there were no bright yellow pigments to make paint. It wasn't until the 19th century, when chrome yellow was manufactured, that Van Gogh could paint the brilliant yellow of his sunflowers. He loved the intensity of this new paint so much, he sometimes ordered 20 tubes at a time. But this new paint was unstable. Chrome yellow reacted with sunlight, changing the structure of the pigment's molecules and the color. Brilliant yellow became dull brown. The paintings lost their brilliance. Today, we see the sunflower painting like this. But to Van Gogh, it was as vivid as the flowers themselves. Decrease the wavelength by just 60 millionths of a millimeter, and the color changes from yellow to green. Green is the color of nature. The color of the pigment in most plants, chlorophyll. Chlorophyll works like all pigments, absorbing some colors and reflecting back others. This time, reflecting green. The green chlorophyll pigment is packed into tiny structures inside the plant cells. Chlorophyll absorbs some colors of light, which gives energy to electrons in the molecule. The plant uses this energy to make food from carbon dioxide and water. But green light isn't used. It's a waste product. It's reflected back out, giving plants their green color. Green pigments are everywhere in the world of plants, but a truly green pigment is very rare in animals. Here's an exception, the turaco. Its feathers contain a unique pigment that reflects green light. Many birds appear green, but their colours don't come from pigments as they do in plants. There are many different ways to create colour. Colour can also be created by the way light reflects off the surface of objects like feathers, or the wing scales of butterflies. We saw that some butterflies get their colour from pigments, but this swallowtail does something very different. To see it, we must zoom in thousands of times. Each scale is covered in tiny ridges, and each ridge made up of layers. These layers are separated by the same distance as the wavelength of green light. The layers reflect light of all colours, but the waves of green light line up together, making the green more intense. All the other colours cancel themselves out and disappear, and we see iridescent green. Every scale on this butterfly wing is sculpted with the same microscopic precision. There is no pigment anywhere, it's just a trick of the light. As the wavelength shortens again, green turns to blue. And we see blue every time we look up. But why is the sky blue? The blue of this dress is created by a pigment, but the blue of the sky comes from a completely different effect. Light passing through the atmosphere is scattered by molecules of gases in the air. The shortest wavelength, blue, scatters more than other colours. Blue light bounces around the atmosphere and seems to come from everywhere in the sky, making the sky appear blue. The same thing happens in some animals. This damselfly contains no blue pigment. The cells just below the surface are packed with tiny particles that scatter blue light in the same way as the atmosphere. The damselfly looks blue for the same reason the sky is blue. A damselfly's bright blue depends on the exact spacing of the particles, and this can only happen when the insect is alive. And there are lots of ways for a damselfly to die. Trapped in a sundew, the damselfly can't escape. As it dies, its cells lose their structure. The particles lose their exact spacing, and the vivid colour quickly fades. But some blues are made by pigments. It's a common pigment today, but in the Middle Ages, deep blue paint was hard to obtain and very expensive, more expensive than gold. In religious paintings, it was usually reserved for the robes of the Madonna. The pigment was made from a rock called lapis lazuli, mined for over 6,000 years in just one province in Afghanistan, and brought to Europe by sea, hence the name ultramarine, beyond the sea. The mines were, and still are, difficult and dangerous to reach, which is why ultramarine was so valuable. Commissioning a religious painting with a lot of ultramarine was a way for a patron to show off his wealth. The paintings themselves became status symbols. There is so much ultramarine blue in Raphael's Madonna in the meadow, Both in the robe and unusually in the sky, it was the equivalent of today's blockbuster movies. Shortening the wavelength again, we move from blue to indigo. This is a color used not for painting, but as a cosmetic. We've been applying color to our skin for thousands of years, and in Europe, indigo was used by the Celts. Indigo dye can be made from several different plants. The commonest in Europe was woad. When the first Romans landed in Britain, they described the natives painting their bodies with woad before charging into battle. Years later, we still dyed clothes with indigo. Until recently, it gave jeans their distinctive dull blue color. Beyond indigo, Newton described the color violet, and beyond that, his spectrum went dark. It remained that way for 130 years, until 1801, when German physicist Johann Ritter shone light on this darkness. He knew that silver chloride went black when exposed to visible light. He was now studying whether different colors had different effects. He projected the spectrum onto paper that had been soaked in silver chloride. He marked the end of the visible spectrum and let the paper react to light of different colors. Silver chloride was least sensitive to red light, reacting more strongly as the light became bluer. But the strongest darkening was beyond the violet end of the spectrum. This must be from invisible light beyond the violet, so he called it ultraviolet. We can't see ultraviolet, but photographic paper can, as Ritter demonstrated. And so can the modern chips in digital cameras. The camera makers normally use sophisticated filters to stop UV. But if we remove these and add one that lets only UV through, we can see the world in ultraviolet. Flowers have very different patterns when seen in ultraviolet. Often the petals reflect UV and the centers absorb it, so the center of the flower appears black. But why are these invisible patterns here? Because they're not invisible to insects. Insects can see UV, and the UV patterns on flowers form targets to guide them to the center where the nectar is. As the insect feeds, the flower is pollinated. A garden looks very different when seen through the eyes of a bee. Birds can also see ultraviolet. And this kestrel uses its UV vision to find the best places to hunt. It hunts for mice and voles, and a field is a good place to look. But this field holds no interest for the bird. It soon leaves to find a better one. How did it know there weren't many mice here? This field is better. and the kestrel can tell from 30 meters in the air. Look at the field through the kestrel's eyes. It's splashed with patches of ultraviolet. This is what it was looking for. The UV patches are made by rodents. The urine of voles and mice reflects UV. And the kestrel can see this. By searching for fields with lots of potential prey, the hunting will be easier. As the wavelength shortens even more, we reach a form of light that even birds and bees can't see. We've now reached the domain of X-rays. And the shorter the wavelength, the more energy the rays have, which gives X-rays some very strange properties. This part of the spectrum was unknown until 1895, when German physicist Wilhelm Röntgen began studying electrical discharges passing through vacuum tubes. As part of his experiments, he passed high-voltage discharges through the tubes. In one experiment, he wanted to stop light from spilling out of the tube, so he covered the apparatus with black cardboard and checked it carefully to make sure it blocked out all visible light. But even with the vacuum tube completely covered, he noticed a faint glow coming from a fluorescent screen further along his workbench. He was intrigued and carried out more experiments. He found that the fluorescent screen was being stimulated by rays that could pass through cardboard. At first, he didn't know what these mysterious rays were, so he called them X-rays. And these rays didn't just pass through cardboard, they could go through human flesh. Placing light-sensitive paper inside a sealed box, he persuaded his wife to place her hand on the box and exposed her hand to X-rays. The developed picture showed that X-rays pass through flesh, but not bone or metal. The first image of a skeleton. X-rays pass through solids because their wavelengths are so short they have very high energy. And these high-energy rays have completely transformed medicine and biology. We can now produce moving X-ray images. A pig eating. A duck eating. And X-rays can be used to create art. Photographer Nick Vesey uses X-rays to create images of everyday objects, quite literally in a new light. He uses technology to make the invisible visible, and the results are startling. Now we take the last step on our journey through ever shorter wavelengths and find rays with even more energy than X-rays, gamma rays. If we could see gamma rays, the night sky would look very different. This is the Milky Way as we see it. And this is the gamma ray sky. A glowing band of gamma rays mirrors the Milky Way. Beyond that, there are other pinpricks of gamma rays. But occasionally, there's a flash brighter than 1 billion suns, lasting just a few seconds. They're over so quickly, it's been impossible to work out what causes them, until the last few years. NASA's Swift satellite is designed to react to a gamma ray burst and swing an array of instruments to face it, in time to record the after effects of the burst, allowing scientists to understand what happened. Some bursts are caused by the death of massive stars. The dying star collapses and emits a stream of particles traveling at nearly the speed of light, which creates the burst of gamma rays. But the shortest and brightest bursts are created when two super-dense neutron stars collide. This collision releases as much energy in 1/10 of a second as our sun in its entire lifetime. Gamma ray bursts are the brightest, most powerful events we know, and they bring us to one end of our journey through ever shorter wavelengths, but not to the end of our story. Now we return to where we started, in the middle of the spectrum, yellow, to make a journey towards ever longer wavelengths. Increase the wavelength of yellow light by a tiny amount and its color changes to orange, and orange really stands out. Nature uses bright orange as a warning. Monarch butterflies taste foul, and they advertise this with their bold pattern of orange and black. This eye-catching pattern is easy to remember. One disgusting mouthful of monarch, and the lesson is learnt. Increase the wavelength once more by just 6 billionths of a centimeter, and the color changes again to red. Like orange, red is very conspicuous. So red sends a strong signal. It can be a warning, but is often more than that. For birds, it's a badge of status, of suitability as a mate. Red pigments are unusual because birds can't make them. They come from their diet. But the pigment structure must be modified by the bird to turn it bright red, and this takes energy. If a bird can afford to display bright red feathers, it must be fit, free of parasites, and an excellent prospect. In the past, it was very expensive to dye a cloth bright red. So red clothing was only for the rich and powerful, restricted to the privileged few. Many countries in the Middle Ages passed sumptuary laws, forbidding people below a certain level in society from wearing bright colors. So, red pigments mean high status, in cardinals in the church, and cardinals in North American forests. Most birds make their red pigments like this. But remember the turaco. We've met the turaco and its unique green pigment. They use the same basic chemicals to make bright reds. These pigments are even more unusual. They dissolve in water, which seems strange for a bird living in a rainforest. But happily for the turaco, the water has to be more alkaline than rainwater before it dissolves the pigment. So for many creatures, including us, red demands attention. Yet the brilliance of red depends on the light level. In bright light, red is a very conspicuous color. In high light levels, the red, green and blue color sensors in our eyes work well, giving us full color vision. All the different colors show up clearly. In dim light, another sensor in the eye takes over. There is only one type of this sensor. It can see light or dark, but not color. But these sensors are more sensitive to light at the blue end of the spectrum than to red. So in dim light, red objects are muted and dull, and blue colors appear brighter. Our own color vision seems vivid to us, but compared to other creatures, it's not very sensitive. Many have color vision more sensitive than ours. In the brilliantly colored world of the coral reef, color is a crucial form of communication. To find prey, find a mate, and for defense. And the champion of color vision is the mantis shrimp. We humans only have 3 different color sensors in our eyes, but mantis shrimps have 16. They can see colors that we can't. The reef world looks very different through a mantis shrimp's eyes. The coral world is so vibrant because it lies in shallow water. Light can't penetrate very far through water, and red light disappears after just a few tens of meters. Yet exploring the ocean deep reveals something very strange. Caught in the lights of a sub, many creatures down here appear red. But no red light reaches this deep. In normal ocean light, they're black and invisible. Red is the longest wavelength that we can see. But the spectrum doesn't stop there. This was discovered by accident in 1800 by William Herschel. He was trying to find out whether different colored light had different temperatures. He used a prism to create a spectrum, as Newton had done, then placed thermometers in each color band and measured the temperature. To check the temperature of the room, he moved one thermometer into the dark beyond the red end of the spectrum. And the temperature climbed above that of the lit thermometers, even though he could see no light. This invisible light became known as below red, infrared. We're going to explore this world of longer wavelengths beyond red, where the waves are invisible to our eyes. Even ordinary cameras can see where we can't. Just as with ultraviolet, modern cameras can sense these longer wavelengths. Camera manufacturers normally stop these rays from reaching the sensor with sophisticated filters. But remove that filter and replace it with one that only passes infrared. The camera can still see the scene, but it's lit only by infrared and looks very different. Plants look green to us because they reflect green light. Yet they also reflect infrared. So to an infrared camera, green vegetation appears brilliant white. Because all vegetation reflects infrared, a satellite that senses infrared can monitor plants from space. This shows areas of vegetation growing and spreading in the spring and summer. We can even see the microscopic plant life in the sea. And we can watch the pulse of the seasons. Increase the wavelength again, and we reach another type of radiation, the far infrared. We can sense these waves. We feel them as heat, and use heat-sensitive cameras to make images of this world. Warm areas show up as bright red, cooler areas as blue. And a cup of hot coffee glows brilliant white. Elephants have big ears, which lose heat quickly, so they show up as cool blue. Our world looks very different in the far infrared. We can see how clothes insulate us. Thicker clothes show up cool blue, while exposed heads and hands glow with heat. The far infrared also lets us see in the dark. The warm bodies of bats stand out in the pitch black of a cave. Move further along the spectrum again, and the wavelength gets even longer. This light has wavelengths from a few millimeters up to a meter or so, more than 100,000 times longer than yellow light, where we began our journey. This is the world of microwaves. Microwaves are familiar. Many of us have microwave generators in our kitchens. They're called microwaves because although their wavelength is so much longer than visible light, they're still only measured in millimeters. But the same rays that heat your pies give us a picture of the birth of the whole universe. If we could see microwaves, the whole sky would glow with them. There are microwaves everywhere in space, coming from all directions. They're left over from the birth of the universe itself. They were created as much shorter wavelength light at the Big Bang, and their wavelength has been stretched as the universe expanded and cooled. There are faint patterns in this microwave background in space, which tell scientists that even from the beginning, the universe was lumpy. These irregularities come from random small differences in the density of the early universe, enough to cause matter to condense. They were the seeds of galaxy formation and the creation of the universe that we know. Microwaves give astronomers crucial evidence for the Big Bang theory of the birth of the universe, but they've also proved useful in other ways. Radar uses waves in the microwave region. It was developed during World War II. At first, it was ground-based, a long chain of tall towers that could detect approaching aircraft. But soon, it was small enough to carry inside aircraft. The apparatus sends out beams of microwaves which bounce off any object they meet. The apparatus can then work out how long it took for the waves to travel out and back, and so how far away the object is. Using radar, bombers could detect targets as small as a submarine periscope poking above the surface. Beyond microwaves, we enter the world of radio waves. Radio waves cover a huge stretch of the spectrum, from wavelengths of 1 meter or so to radiation with wavelengths of over 100,000 kilometers. We're used to thinking of radio as something we listen to, but that's because the sound from the speakers has been sent to the radio set by wireless, radio waves from a transmitter received by the set's antenna. But radio waves are as much a part of the spectrum as visible light. Radio sets receive waves from a transmitter, but we can build equipment that detects natural radio waves from deep space. These are radio telescopes, and the bigger the dish, the better the resolution. With radio telescopes, a truly enormous dish size can be created by linking together lots of smaller dishes. This is the ALMA radio telescope, perched 5,000 meters up in the clear, dry air of Chile's Atacama Desert. Eventually, it will have 66 dishes all connected, the most advanced telescope on Earth. The equivalent of a single dish about 1.5 kilometers in diameter. ALMA will allow us to peer deeper into the universe than ever before. This is the most distant object we can see, a quasar. It's a special type of galaxy, and we first found them by their radio emissions. Quasars are very distant galaxies, some 12 billion light-years away. And there's a reason why we can see these objects at the very edge of the universe. At the center of a quasar is a supermassive black hole, which is consuming matter. The largest quasars devour the equivalent of 300 planet Earths every minute. And as they do, they release huge amounts of energy. This is the source of the radio waves that led to our discovery of quasars. We now know that quasars emit radiation right across the spectrum, from radio waves through visible light to X-rays and gamma rays. And this is where our journey through the spectrum ends, at the edge of the universe, with the most distant objects we can see. A journey that began with Da Vinci now extends to the furthest reaches of the universe. And with that we have, for now at least, reached the limits of our knowledge and the limits of light.